Now we'll put the values of x1 double dot, x2 double dot, x1 and x2 in equation number 2. What is equation number 2? Equation number 2 is the matrix form of the equations of motion. So in that matrix form of the equations of motions, we'll put x1 double dot, x2 double dot, x1 and x2. And also we'll take this omega n1 to be equals to omega n2. The same assumption which we have taken in equation number 1. And that should be equals to omega. That we'll put. Okay, so the matrix form of the equations of motion is the mass matrix m1 0 0 m2 multiplied by the column matrix of x1 double dot and x2 double dot. So instead of x1 double dot, I'll write minus omega square a1 cos omega t. Instead of x2 double dot, I'll write minus omega square a2 cos omega t plus the stiffness matrix 1 plus k2 minus k2 minus k2 k2 plus k3 multiplied by the column matrix x1 and x2. Now what is x1? a1 cos omega t. What is x2? a2 cos omega t. And that should be equals to 0 column matrix. Okay. Now here from the first and the second element of this column matrix, I can take minus omega square as common. So I have taken minus omega square outside. So it will be m1 0 0 m2 and here it will be a1 cos omega t and a2 cos omega t plus the stiffness matrix is as it is. The column matrix of a1 cos omega t, a2 cos omega t is as it is, and that should be equals to 0 column matrix. Okay. Now I'll multiply this minus square to this matrix. So remember in matrix multiplication, if you are multiplying the entire matrix with a constant term, each element of the matrix is getting multiplied by the same constant term. That is the rule of the matrix multiplication with a constant. So if I want to multiply this minus omega square to each element of this matrix, the each elements will be multiplied by the minus omega square. Okay, so minus omega square into m1, 0 into minus omega square is 0, again 0 into minus omega square is 0, and minus omega square into m2. Okay, plus here this will be the stiffness matrix k1 plus k2 minus k2 minus k2 and k2 plus k3. Now once I'm getting these forms, I can take a1 cos omega t, a2 cos omega t column matrix common from both matrix, right? So that is what I have done here. Out of this matrix and the stiffness matrix, I have taken a1 cos omega t, a2 cos omega t column matrix as common. Okay, and that should be equals to 0 column matrix. Now the order of this matrix is 2 by 2, 2 cross 2 matrix. The order of this matrix is also 2 cross 2. So I can add both the matrix. The order of this matrix is 2 cross 2. The order of stiffness matrix is also 2 cross 2. So I can add both the matrix because then there is a plus sign. So if I want to add both the matrix, each element of the first matrix will be added to the corresponding element in the second matrix. So minus omega square m1 will be added to k1 plus k2. 0 will be added to minus k2. Likewise, I need to write. So I have written minus m1 omega square plus k1 plus k2. Here it will be 0 plus of minus k2. So it will be minus k2. Here also it will be 0 plus of minus k2. So here also it will be minus k2. Here it will be minus m2 omega square plus k2 plus k3. Now this entire matrix should be multiplied by the column matrix a1 cos omega t, a2 cos omega t, and that should be equals to 0 column matrix. Okay, now Here what I have done, here in this column matrix, again cos omega t is there in two terms, so I'll take cos omega t as common. Now here the cos omega t will be taken as common thing, so what we can do, we can divide the zero column matrix by the term cos omega t from here. Again it will be zero column matrix only, because that cos omega t will be divided by each element of this zero matrix. So that will be 0 by something will be 0 only. So it will be 0 matrix only. Now here it will be minus m1 omega square plus k1 plus k2 minus k2 minus k2 minus m2 omega square plus k2 plus k3. Here it will be a1 and a2. Now this matrix, this displacement matrix will be reduced to a1 a2 only, because cos omega t I have taken as common, and here it will be equals to 0 column matrix. Now here I'm getting the product of two different matrices. First matrix is this one of the order 2 cross 2. This matrix is of the order 2 cross 2. And the second matrix is this one, A1, A2. This matrix is 2 cross 1 matrix. Now, the product of these two matrices must be equals to a 0 column matrix. And the order of the product of these two matrices will be 2 cross 1. Right? Now, if I want to have the non-trivial solution of the product of two matrices, and because the product of two matrices is equals to a zero matrix, so that means determinant of any one of the two matrices is equals to 0. Remember, the product of two matrices are equals to 0 matrix here. What is the meaning of that? It means the determinant of any one of these two matrices is equals to 0. Now, we'll take this matrix first, 2 cross 1 displacement matrix first. Can the determinant of this matrix A1, A2 will be 0? Yes, we can assume it to be 0 because this is the solution part. We have already assumed a solution. So we can once again assume the determinant of this matrix to be 0. But that will be a trivial solution. That will not give us anything. No information will be there if we'll take the values of this determinant a1 a2 to be 0, and again the determinant of a1 a2 is not at all possible, because we know the determinant exists only for a square matrix. It's not an x square matrix, so its determinant will not be exist. Now talking about this matrix, it's a 2 cross 2 matrix, so its determinant will be existing and its determinant may be 0. So we'll get the first non-trivial solution in which the matrix this one will have a determinant equals to 0. So we'll write the same thing. Determinant of the matrix minus m1 omega square plus k1 plus k2 minus k2 minus k2 minus m2 omega square plus k2 plus k3 is equals to 0 we have taken. So we'll write that matrix in determinant form. Now we'll solve this determinant. So solving this determinant, we'll get minus m1, this is minus m1 minus m1 omega square plus k1 plus k2 multiplied by minus m2 omega square plus k2 plus k3 minus of k2 square equals to 0. Now this equation is called as the characteristic equation. This equation is called as characteristic equation. The roots of this characteristic equation are called as eigenvalues. Remember, the roots of the characteristic equation are called as eigenvalues. Now what will be the roots of these characteristic equations here? The roots will be the values of omega square. Right, the roots of this equation will be the values of omega, sorry, not omega square, omega. The roots of this characteristic equation will be the values of omega. That means the values of omega will be the eigenvalues, right? Because we know the roots of characteristic equations are called as the eigenvalues. So the values of omega will be eigenvalues. Now we'll take the other view also. See if you can remember from equation number 3 we have the value of a2 and a1 and we got two distinct values of a2 and a1. In first formula a2 by a1 was equals to minus m1 omega square plus k1 plus k2 by k2, and this second formula for a2 by a1 was k2 by minus m2 omega square plus k2 plus k3. Now because both are the formula for a2 by a1, so we can take a2 by a1 equal from the equation number 3. Now I'll put the first formula for a2 by a1 and that should be equals to the second formula of a2 by a1. So from here also if I'll solve this, once again I'll get the same equation, the same characteristic equation I'll get, which earlier I got. See here, this is the characteristic equation, and by taking a2 by a1 formula equal, we'll once again get the characteristic equation, the same characteristic equation. Now the thing is we got the same characteristic equation and we need to solve the characteristic equation in order to get the natural frequencies of the system, the values of omega. Now we'll solve the characteristic equation. So we'll get m1 m2 omega to the power 4 minus m1 omega square into k2 plus k3 minus m2 omega square into k1 plus k2 plus k1 plus k2 multiplied by k2 plus k3 minus k2 square equals to 0. This is the solution part of the characteristic equation, right? Now in order to understand the calculation of natural frequencies and other concepts also out of this modal analysis, we'll take a simple example from the book S.S. Rao. So I have taken the example number 6.16 from S.S. Rao book. You can also refer the same example in which they have given the values of m1, m2, k1, k2, k3. m1 is equals to 10, m2 is equals to k, k1 is equals to 30, k2 equals to 5, k3 equals to 0. Remember, I have not written the units of mass or the stiffness. Why I have not written them? Because the terms are relative to each other. If I'm talking about two masses, m1 and m2, they are relative to each other. If the unit of the mass is kg, so m1 is 10 kg, m2 is relatively 1 kg. If the units of the mass are gram, so m1 if it is 10 gram, m2 will be 1 gram relatively. So they are relative, so no need to write the units. Same thing applies to stiffness also. If I'm taking the stiffness unit to be Newton per meter, so K1 is 30 Newton per meter, K2 is 5 Newton per meter, K3 is 0. If I'm taking the units to be Newton per mm, so K1 will be 30 Newton per mm, K2 is 5 Newton per mm, K3 is 0. So all are relative to each other. That's why they have not mentioned the units. Now they have mentioned some initial conditions also. So these all the things are part of the same given data out of the same example 6.16. So initial conditions, what they have mentioned, x at 0. That means the matrix x1 and x2 at 0 at time t equals to 0 is 1 0. That means x1 is 1 at time t equals to 0, x2 is 0 at time t equals to 0, and x dot at time t equals to 0 seconds is equals to 0 0. Means x1 dot at time t equals to 0 is 0, x2 dot at time 0 is equals to 0. These are the initial conditions given in the same example. Now I got the characteristic equation solution part. So here I'll put the values of m1, m2, k2, k3 and k1. So I put these values out of the example. I put these values here. You can see I put the values here. So only left variable will be omega square. Other things are known. Okay. Now here we'll get the quadratic equation of omega square, not omega. Remember, this is the quadratic equation of omega square, not omega. So we'll solve this quadratic equation for the value of omega square. So the simple formula which we have learned in our primary schools will apply the same formula. The omega square will be minus b plus minus square root of b square minus 4ac by 2a. So minus here the b coefficient is 85, a coefficient is 10, c coefficient is 150. So it will be minus 85 plus minus square root of minus 85 square minus 4 into 10 into 150 whole divided by 2 into 10. Okay. So here I'll get the formula in the form of 85 plus minus 35 by 20. Now we can see we'll get two different values of omega square. The first value of omega square will be omega 1 square equals to 85 plus 35 by 20. The second value of omega 2 square will be 85 minus 35 by 2. If we'll solve both of them, we'll get omega 1 square to be 6, omega 2 square to be 2.5. And we'll take the square root of 6 and the square root of 2.5. So we'll get omega 1 to be equals to 2.449 and omega 2 to be equals to 1.581. Once again, remember, both are relative to each other. If I'm taking the unit of omega to be radian per second, so omega 1 is 2.449 radian per second, omega 2 will be 1.581 radian per second. If the unit of omega you are taking as radian per minute, so omega 1 will be 2.449 radian per minute and omega 2 will be 1.581 radian per minute. Now what are these omega 1 and omega 2? Remember, the omega is the natural frequency of the 2 degree of freedom system which we have taken. And initially what we have assumed, omega n1 to be equals to omega n2, and both are equals to omega. We have assumed that. But here we are getting two distinct values of omega. Omega 1 is 2.449, omega 2 is 1.581. That means there are two natural frequencies of the given 2 degree of freedom system. And that is obvious. We know if a system is having 1 degree of freedom, its natural frequency will be 1. The number of natural frequency will be 1 and the number of equations of motions will also be 1. If a system consists of 2 degrees of freedom, that means there will be 2 equations of motions for the system and there will be 2 natural frequencies of the system. Likewise, if the degrees of freedom of a system is n, so there will be n number of equations of motions and there will be n number of natural frequencies. So here we are getting 2 natural frequencies.